Hi everyone, and welcome back to Fundamentals of Engineering with Farhad, Geotechnical Engineering, Soil Mechanics. In this video, we want to talk about two important geometrical coefficient in grain size distribution curve of a soil sample, and they are C sub U and C sub C, uniformity coefficient and coefficient of curvature, which we talk about them in few in few minutes. So in our chart, the horizontal axis is the grain size distribution and the vertical one is the passing rate of that soil from the sieve. D sub I or DI stands for diameter of a soil sample, which I% of that passing through the sieve size. If this is our soil distribution sample with extended S shape, we want to know the formula and the mass behind and also the conceptual meaning of the Cu and Cc. So the formula for coefficient of uniformity is d6t over d10, and that's uniformity coefficient, and C sub c stands for coefficient of curvature, and the formula for that is d30 squared over d10 times d60. We'll talk about them in a bit. Let's jump to the first coefficient, which is Cu. Cu is d60 over d10, and that stands for uniformity coefficient in the soil sample. So if this is our grain size distribution, which is an almost extended S shape for first soil, and then we have the other sample, which is the second soil, first one and the second one. So for the first one, we have like a D60, D10, and D60. And for the second one, the second soil, we have like D10 and D60, which you can easily see how they are closer to each other. As the D10 and D60 get closer and closer to each other, the distribution curve is just moving to a uniform, almost uniform size sample, which is not a good case in our sample. We want to have a soil sample which includes almost all kind of distribution soil sizes. So in that terms, the conceptual meaning of uniformity coefficient is Cu, for example, for 1 is d60 over d10, and for second sample, you can easily see how d60 decreases from the first and d10 is increasing from the first sample, and so the C sub u for second distribution is decreasing, and the meaning of that, we need to have like to avoid the having unisized grain in our soil sample, we need to have our Cu greater than a specific number and C sub u greater than 4 in gravel, and also C sub u greater than number 6 for sand. We'll talk about that as well. And the reason for that is avoiding the uniform size sample in our soil. For gravel, Cu should be higher than uniformity coefficient should be higher than 4, and for our sands, C sub u should be greater than number 6. And in terms of the visual part of that, it just says for gravel and soil sample are kind of more extended, should be more extended in terms of the gravel. That Cu bigger than 60 should have a more variation in size for sand sample of a soil. And the other coefficient is the coefficient of curvature C sub c, and the formula for that is d30 squared over d10 times d60. And again, if we have like our normal sample, which is like extended S shape, we can easily see our C sub C, which stands for coefficient of curvature, is the ratio of d30 squared over d10 times d60. Now assume that we have like two other samples. The first one, number one, is a convex case, and case number two is a concave, and our original one was a zero, case number zero. So you can easily see in terms of the coefficient of D30, D60, and D10 for our three samples, you can easily see how their D60, D30, and D10 for these three shapes varies for both original case convex and concave sample. So it just says for our CC for the first sample is equal to D30 square over D10 times D60, and our original sample, which is CC sub 0, that's again the same formula. And for the second sample, C sub C2 is again the same formula, but the difference for them is the CC0 is higher than the CC1 and then less than CC2. And let's see what's happening there. In the first sample, in the convex shape, D30 is decreasing from the original one, and in the second case, which is a concave one, D30 is increasing. So it just says if we want to avoid our sample from moving toward the smaller sample size in a convex shape, as you can see here, we should have our C sub C higher than numeric value of 1. So that's for this part. Avoiding having a convex shape which is move let the grain size moves toward the smaller grain size. So if this is the case, this is our CC1 for the convex shape, and that's why CC should be higher than 1. On the other hand, though, for the second part, if D30 increased from the original one, CC2, it just D30 increases, and it just result the sample moving toward the larger size sample. So that's why we need to hold our horses and take the second graph toward the first one. So it just says we need to avoid having two and avoid having one by getting the second graph toward the original one, and also move the convex one toward the um, original one as well. So that's why we need a C sub C, or coefficient of curvature, less than 3. So it means for a well-graded soil sample, we need to, if we have like C sub C less than 1 in a convex shape, it just moves toward, our sample moves toward the smaller size grain. And if our C sub C higher than numeric value of 3, it just move toward the larger size grain, which is not acceptable for a well-graded soil. So that's why our C sub C should remains in the domain of 1 and 3. C sub C should be higher than 1 and less than 3. That's the conceptual meaning behind the curvature coefficient as well as the uniformity coefficient. Thank you. We'll solve more problem related to these geotechnical concept in next videos.